So the intention of this particular video is to talk about all the practical aspects of the theory topics that we've covered. So in this particular video, everything that we've seen in theory, we are going to put that to practical use. So let's get going. So in this video, we'll first talk about So these are the topics that we are going to cover in this particular video. We'll first start talking about what is old API and new API. We'll then see how to go about writing your MapReduce code with the new API. We'll then talk about how to go about writing your code using the old API. We'll then talk about what is the difference between old API and new API. We'll discuss what is toolrunner. We'll talk about what exactly is distributed cache and how do you basically put to use. So we've already in theory seen what is toolrunner and distributed cache. We'll then talk about what exactly is or how exactly to go about writing a partitioner, how exactly to go about writing a combiner, how to go about writing custom writables, and how to go about writing inverted index. So this is the agenda of this particular video. So before we jump into any of these, let's talk about what exactly is old API and new API. Now there are two parallel worlds running. So a lot of times you would hear people talking about new API means Hadoop 2.x. Well, that's not really the case. So in one parallel world, developers were working on Hadoop 1.x. and they decided to enhance it by making it Hadoop 2.x. In the parallel world, developers were working on old API and they decided to enhance that by writing the new API. Basically, these two tracks had nothing to do with each other. Hadoop 1.x and 2.x was all about moving from job tracker and task tracker and going to yarn. Old API was a way to write code, and in new API the signatures have changed. The important point is you can perfectly write old API code on Hadoop 1.x as well as 2.x. And you can perfectly write a new API code on Hadoop 1.x as well as 2.x. It's perfectly acceptable. So Hadoop 1.x and 2.x and old API and new API are two different tracks and they don't have anything to do with each other. That's the real point. So now let's look at how do you go about writing your MapReduce code with the new API as well as old API, and then let's discuss the differences between them. Let's get going. So let's first log in to the VM. Let's create some data. So if we are planning to write some code and run it, let's first create the data because we will be running our MapReduce code against that particular data. So let's go to terminal and let's create some data. So we've created the first a folder called as Mapreduce input. In Mapreduce input, we are going to dump some data. So let's create that data. In exercises folder, we will already find that there is a file called as shakespeare.txt.gz. Let's unzip this file and let's dump that to HDFS. So what we see is we have a file called as shakespeare.txt. Let's dump this file into HDFS, and this will be used for all our examples. We'll be running all our examples against this particular file. So we've dumped this file to HDFS. So what we see is shakespeare.txt in here. Now that data is prepared, let's basically understand some code and run that code. So let's go to Eclipse. That's where all our code will be. Now our Eclipse is picking up code from home training workspace. So you can very well visit let's go to home training, and these are all the code examples that are available for you, and we are going to take some of them and see how to make it work. So the first example that we are going to pick up is word count new API. So the name of the project is word count _ new API. So once we import this example, what we see is we see set of errors. Reason being, we still haven't imported the libraries. So before we do a code walkthrough, let's first import these libraries so that we see the entire project to be error free. Once we have that, let's understand the code line by line, and then we will run this code with the new API. So let's understand how to import libraries. Right click, properties, Java build path. First get the JRE system library. So that's the first library that we need. We need the JRE. Next, we are supposed to import Hadoop specific libraries which are available in user lib folder. So we click on add external jars, user lib. Let's first take all the Hadoop libraries. Next, let's take all the Mapreduce specific libraries. And third, let's take all the yarn related libraries. Once we do that, what we see is that all the errors are gone. All the errors are gone. So that makes our project error free. And now we are in a position where we can understand the code line by line. Once we understand the code line by line, the next task will be to execute this code. To execute this code, we will be exporting this as a jar file and running it. So let's first understand the code line by line. Typically, every Mapreduce program would have 3 Java classes: the main class, the mapper class, and the reducer class. In our example, word count is the main class, word mapper is the mapper class, and sum reducer is the reducer class. So let's understand it with the main class first. So every Java program typically starts with set of import statements. Here we have set of import statements which will be imported based on our requirement. The main class that we have is called as word count. The main class that we have is called as word count. Every Java program begins with the main function, and here we have the main function. Now within main function we have first set of code where we are expecting 2 arguments. So it's like we developing the code and we setting the expectation that for our job to be executed by anybody, we minimum need 2 arguments. So it's commented out here. As a developer, we are setting an expectation that anybody who would like to run our program has to provide 2 arguments, input path and output path. Failing to do so would basically stop the program, would stop the execution of the program, and the job will not run. So here we are using a job class. Now when we are submitting this code, we will be creating a jar file and we will have to communicate it to the cluster that in our jar file there could be hundreds of Java classes. The main class that is required is word count.class. So this is our way of communicating that the cluster or to the cluster that word count is the main class for this particular program. Word count is the main class for this particular program. In the next statement, we are setting the job name to be word count. This is our way of communicating to the cluster that as per us, we are going to call this job as word count, and this will also help us trace when the job runs on the cluster. So it will make it really easy for us to trace when the job is running on the cluster. The next couple of code or couple of sentences or lines of code, we are setting the fact that the first argument that the end user provides is going to be input path and the second one is going to be output path. So when we receive two arguments, this is our way of saying that the first argument has to be treated as an input path and the second argument has to be treated as an output path. So you have set input path and set output path. In the next few lines, we are communicating it to the cluster that the mapper class that we have is called as word mapper and the reducer class that we have is called as the sum reducer. So mapper class is word mapper and the reducer class is sum reducer. And then it's time to set the types. Before we jump into types, let's quickly summarize it. We first start with the main class. In the main class, we are communicating to the end user, whoever is calling our code, that we would expect 2 arguments for this particular job. First one is going to be input path, second one is going to be output path. Otherwise, the program is not going to run. We initialize a job and then we say that if we submit a jar file which will have hundreds of Java classes, we are telling the cluster that the class that is our main class is called as word count.class, and we are giving it some descriptive name so that we can easily trace this from the browser. In the next few lines, we are conveying that the first argument that we've received from the user has to be treated as an input path. The second argument that we get from the user has to be treated as output path. In the next 2 lines, we are in forming the cluster that the mapper class is wordMapper.class and the reducer class is SumReducer.class. In the next two lines, we are setting the output key class and output value class. Let's understand what it does. These two lines are our way of conveying that mapper output key class and reducer output key class is text. So when we just say set output key class, that means for the mapper output as well as the reducer output, the key class is going to be text. Text is nothing but string that is serializable, so that for shuffle and sort the boxing is done. And the mapper output value, so for the mapper input, for the mapper output key and reducer output key, we are using text. For the mapper output value and reducer output value, we have decided to be int-writable. If you carefully observe, our Mapreduce code works in such a way that mapper output is hi1, how1, r1, u1, which is nothing but text comma int-writable, as well as the reducer output is hi comma 4, how comma 4, and so on and so forth, which is again text comma int-writable. So in two lines itself, we are conveying that for the entire job, the key class is going to be text, that is mapper output as well as reducer output, and mapper value output as well as reducer value output is going to be int-writable. Once we've set all the expectations, it's time to submit a job. This is how we submit a job. And that brings us to the end of the main class. What we observe in the main class is that main class is simply an expectation setting class. In real world also, what you'll observe is the main class nearly would remain same for all your jobs. It will rarely change. And if something changes, it will be typically only the types. That's why the main class is also sometimes referred as expectation setting class. Expectation setting class. Now, this is our main class. The framework would first call the main class and eventually move to the mapper. So this is where we are. This is our mapper class. This is our mapper class. In our mapper class, the name of our class is wordMapper, and we've set that expectation in the driver class. The mapper class extends from a mapper, and we see this signature. Let's understand the signature. So this particular class is our wordMapper class. It extends from mapper parent class. So the wordMapper class extends from the mapper parent class. And the four data types that we see, long writable, text, text comma int writable, is our way of saying mapper input key, mapper output key. So the format is mapper input key, mapper input value, mapper output key, and mapper output value. So this is our way of conveying that mapper input key is long writable, which is the byte offset. Mapper input value is text, which is, let's say 0, hi, how are you, which is an input. Text again here is output of the mapper, which is hi, 1, how, 1, which is hi or how. And int writable is hi, 1, so that 1 is nothing but int writable. So long writable is mapper input key, and in our case it is the byte offset. We've discussed that in the word count explanation. Text is the entire line. The second text that you see is nothing but it's the output that comes from the mapper, and int writable is the output value of the mapper. So 0, hi, how are you is nothing but mapper input key and value. Hi, 1, how, 1 is nothing but mapper key value pair output. So this is how you go about writing your or setting expectation of your mapper. Within the mapper, we have the map function, which receives one record at a time, And again, the signature here is The map input key is long writable, which is nothing but the byte offset, and the text value is nothing but the entire line. So the input to map would be 0, hi, how are you, for example. Context is basically a class that is used for two purposes. First, it gives us the statistics for a job, the number of bytes read and written. Second, what it gives us is it helps us write the intermediate output to the local file system, the mapper intermediate output. So what we do within the map function is we are converting a line to string. So basically, hi, how are you, which is right now coming in as an object, would be converted as string. So in here we have the entire value, which is line variable, and we are splitting the line by word. That means 0, hi, how are you becomes hi, how are you. So the value is hi, how are you. Once we've set that expectation, what we do in the for loop is, for each word, if the length of the word is greater than 0, we will simply emit word, 1. So the output of mapper would look like hi 1, how 1, r1, u1. That's how you get your output. This is how we go about writing our mapper. Map function takes one record at a time, and it can give out multiple key value pairs at a time. In our example, map takes hi, how are you, and the output is hi 1, how 1, r1, u1. That's how we get our output. The next class that gets called, so after entire mapper is done, there is shuffle and sort, and after shuffle and sort, what gets called is the reducer. Remember, we are not really supposed to code the shuffle and sort. We are, as a developer, majorly focused on two things: writing mapper and writing reducer. So now let's look at how does reducer look like and how does reducer work. So the class name is SumReducer. We've set that expectation in the main class. So we say public class SumReducer extends the reducer base class. Text, int writable is the input key value pair, which is hi, 1. And text, int writable in the second case is hi, 4, how, 4, which is nothing but the reducer output. So the SumReducer class has the business logic for the reducer. It inherits from the reducer base class. Text, int writable, it's our way of saying text. The first text is the input key to the reducer, example hi. Int writable is the input value to the reducer, which could be 1. Text is the output key of the reducer, which is, let's say, hi, and int writable is the output value for the reducer, which is, let's say, 4. So my input could be hi, 11111, and output is hi, 4. That is possible. So this is the signature for the SumReducer. Let's move to the next thing, which is the reduce function. In the reduce function, what we receive is a key and list of all the values. In a reduce function, what we receive is key and list of all values. So let's say hi, 111111111. This is the input that we give to the reduce function. In the reduce function, we are receiving key as input, which is hi, and an iterable on list of values. So it's hi, 11111. So we are getting an iterable on top of it. So we start with int word count is equal to 0. So this is a variable that will count the words. So it's int word count is equal to 0. For int writable value in values, we simply want to add the word count. So we keep on adding 1 plus 1 plus 1 plus 1. At the final, what we write is context.write is equal to key, int new writable word count. So the output of reducer would be high comma 10 in this particular example. So what we've successfully seen is, or this is how we get our output. So what we've seen so far is how to go about writing your main class, how to go about writing the mapper, and how do you go about writing the reducer. How do you go about writing the reducer? This is how you write your word count program using the new API. So quick summary. In the driver class, you set the expectation as to which is mapper, which is reducer, what arguments we are supposed to receive, and on what basis or what treatment we are supposed to give to the arguments. In the mapper, we look at how to deal with one record at a time, and in the reducer we take one bucket at a time. So it's high comma 1 1 1 1 10 times. What you get is high comma 10. That is how MapReduce works from the new API perspective. Now let's look at the same code in the old API and let's compare old API versus new API. So we are importing a new project which is word count underscore old API. Again, we have list set of errors. Now we are first going to remove all the errors one by one. Start with user lib Hadoop. So we've taken user lib Hadoop and user lib MapReduce. It's now time to take user lib yarn. So we've successfully imported all the required libraries for the old API. Now let's understand the code, and after that we will run our code with old API as well as new API. So here we have word count. Again, the same thing, that we are having two arguments. Now here we see run method, but this run method is not because we are using old API, but because we are using tool runner. In the next section, we'll also talk about what exactly is tool runner. So tool runner is optional. In this case, we are using tool runner. In the next example, we'll see what exactly is tool runner. But what we observe is the only change here is the first few lines is basically accepting two arguments. So this is same as the previous one. Here we are setting up another object called as jobconf, whereas there we are using job. Setting up input path and output path is absolutely identical. And then we are setting up the mapper class and reducer class. The mapper class is wordMapper.class and the reducer class is SumReducer.class. Now here is a classical example where instead of directly writing set output key value class which will apply to mapper and reducer, here we have chose to go in a different way. We are separately setting the output types of mapper and separately setting the output types of the reducer. So set map output key class is text, comma and writable, and set output key class for the reducer is text, comma and writable. So we could have very well clubbed it as set output, but just to demonstrate, we've separated them here. and then we run the job. So this is how you go about writing your old API. Let's quickly look at the mapper and reducer class, and then we will compare the differences between the old API as well as the new API. So here we have the old API code. Here we are having a class called as word mapper. So word mapper is the class. It extends from Mapreduce base and implements mapper. It implements mapper. In the map function, what we see is long and text is same, just that we see instead of context, output collector and reporter. So in the new API, context will take care of output collector and reporter, whereas in old API we had two classes. Output collector will write the output of the mapper to intermediate file system, and reporter will basically give the context or give the counters for the job as to number of bytes read and so on and so forth. The business logic remains the same. We split the string and we are emitting word comma 1. In the reducer also it's exactly same. Notable differences are the reducer also extends from Mapreduce base and it implements the reducer class. Now when it comes to the reduce function, we exactly have the same business logic, just that here also we observe that there is output collector and reporter, whereas in the new API we have just the context. So these are the notable differences between old API and new API. Let's quickly summarize them and let's talk about running these word count programs. So we have new API and old API. In new API we have context. In old API we have output collector. And reporter. So both the things that output collector and reporter they do individually, context does that here. We use job class. And here we use job conf. Here we basically extend So new API prefers inheritance over interfaces. So these are the major differences between new API and old API. They are majorly from the signature perspective. Now let's try running a Mapreduce code with the new API as well as old API. What we'll observe is everything is going to remain same. It's just that you are using old code or new code. So let's run this particular code. So let's get here. We open Eclipse. Now first we are going to see how to run a program for the old API, and then we will see how to run it for the new API. Now when you see that, what you're going to see is that, well, it's code and we will bundle it in the same way and we'll get the same output with subtle differences in the way output is displayed. So let's get started. So first let's open Eclipse. So let's run our code on Mapreduce input folder. So let's run our code on Mapreduce input folder. So let's take old API, right click and export it as a jar file, because for Hadoop you will need a jar file to be created. So word count underscore old API.jar is what we are creating in home training folder. Let's create it and bang. When you do lsltr, you see word count old API.jar. So let's execute this particular program. Say Hadoop jar word count old API.jar. So first, Hadoop is a command. Jar is an option which tells that we wish to run a jar file. Word count underscore old API is basically the jar file. In that particular program, our main class is word count, W capital C capital. That's our main class. And now it's time to give input path and output path. So it'll be Mapreduce underscore input old API underscore output is what we are expecting our output to be. Let's run this program. So now the program is submitted with an application ID. We can trace this from here. We've submitted this application. It's still running. It's finished. Click on history and we see there were 2 mappers and 1 reducer which ran for this particular application. And there were 2 successful mappers and 1 successful reducer. In Hadoop FSLS, you see old API underscore output. And the underscore success conveys us that the program was successful. Now this success could be seen as a flag. So when we let's say automate the entire process, if we see success file created, that means everything was successful. Now it's time to see our output, and this is where we have our output. This is where we get our output. Now what we are going to do is we are going to see how to run code for the new API. It's all going to be same. Just one thing we need to observe is when the output file gets created in the old API, the name of the file has a naming convention part 00000. So if there are 6 reducers, we'll see 6 output files. The next thing we are going to do is run this with the new API. So say export. We'll say finish. We've created a new API jar. So here it is, new API. Everything remains same. Submit the job, and the job gets submitted with a job ID 007. What we see here is that the output would be same, just that when you have new API running, you would have the naming convention of output as part-r00000. What this conveys is that part is the part file, R means there was reducer. If there was no reducer, we would have got part-m and the naming convention. Here we have part R, that means there was one reducer that ran and we got our output. So this is how we run our word count program with the old API or new API. Now, irrespective of the code you write, this is how you typically run jar files in Mapreduce. So this is how you run old API and new API. So what we've seen so far, we've seen what is old API and new API. We've understood the differences between the old API and the new API. We've understood word count using the new API. We've had a complete code walkthrough of the new API. We've seen word count with the old API. We've seen the differences between old API and new API. And we've seen how to execute a Mapreduce program. The next topic that we are going to talk about is tool runner, but before that, let's quickly summarize and make notes here. We've seen how to write code in new and old API. We've seen the differences and we've executed a word count program. So the next thing we are going to see is tool runner. So let's quickly recap what is tool runner, and then we will understand the code for tool runner. So you have cluster, you have your client. Just for an example, the number of reducers is 1, and when you submit your code, you would want number of reducers to be 6. What we'll do is, when we submit a code, we'll submit that in the command line, and that would ensure that the number of reducers are 6. And that is possible because we have tool runner. So let's quickly first walk through what exactly is tool runner in the code, from the code perspective, and then we'll run the code. So the old API is using tool runner. We can use this in new API also. The main class actually gets executed on the client, on your laptop. So when the main class is getting executed, by default, let's say the number of reducers is 1. but then we give opportunity to the developer by calling toolrunner. What toolrunner does is it passes the object for this particular class for calling back, and it passes the argument. And in this run method, we will take any argument that the user wants to customize, and for this particular job, it will be applied. What that means is, by default, the number of reducer is, let's say, 1. Now what we would want is, we would want to run this with number of reducers as 6. So we can customize that from the command line and we can make this work. Let's understand this one by one. So let's say we run code for old API. So we run Hadoop jar word count old API.jar word count old API input or output without toolrunner. Let's demonstrate this. So we are running this program. The job ID is 008. But what's of interest to us is how many reducers or how many output files do we get out of this? That's something of interest to us. So the job has run. So when we run Hadoop FSLS, we see that there is one output file which is around 30 MB. What we've seen right now is we have one reducer by default. Now let's customize that. So we say Hadoop jar word count old API.jar word count -d mapred reduce tasks is equal to 6 Mapreduce input and old API output with toolrunner. So the job ID that we get is 009. The job gets going. So the job has got submitted and we've seen it to be successful. Let's understand how it looks on the UI, and we will see the output. (009) job has succeeded. And what we see is that the number of reducers is 6. By default, the number of reducers is 1, and we've been demonstrating that. But here we decided to customize that behavior by saying, look, the cluster is running with 1 reducer. We would like to run it with 6 reducers, and it will respect that fact. Let's look at the output right now. We can see output from the command line as well as the UI. Say browse the file system, user training with toolrunner, and we see there are 1, 2, 3, 4, 5, 6 output files. There are 6 output files. And if you look at the naming convention, it's part 000, 001, 002, 003, 004 and 005. That is how you can customize a default behavior from the command line, and ToolRunner does the trick. So this piece of code here, which is optional, does the trick here. If you look at the new API, let's say we are not using it. So if you see in the new API, we are not at all calling the new API. Here we are directly interested in calling main and starting the program. So that is how ToolRunner is used. That is how ToolRunner is used. So let's summarize ToolRunner. ToolRunner is a facility that lets you customize a certain behavior from command line. By default, the main class of a Mapreduce program gets executed from Hadoop client. So the main class actually reads all the Hadoop configurations and applies them. And a ToolRunner gives us a facility that we can actually customize a certain behavior. And in our example, we took number of reducers as by default it is 1 and we took it as 6, and we demonstrated that the number of output files were 6. That is how we use ToolRunner. That is how we use ToolRunner. So a quick summary of this video. What we've done is we've understood what is old API and new API and Mapreduce, and old API and new API has nothing to do with Hadoop 1.x and 2.x. We've seen what is old API, what is new API, how to run them, and then we've seen what exactly is ToolRunner. The next topic that we are going to discuss is distributed cache. If you recall, in the theory section, we've seen distributed cache is a way to pass some lookup data. It's a way to pass some lookup data. So let's take example of our own Mapreduce program. Now the word count program is basically giving us output or word count for each and every word. Let's say we want to exclude some set of words. Let's say stop words like the, if, of. So let's see if we can exclude them. Let's understand this with an example, and then we'll summarize this. So let's first start by importing the project. So we have this project included for you called word count _ distributed cache. Let's first import the libraries. let's first add the library, and let's add external jar, so it's user lib let's get yarn, so all the errors are gone. Now let's try to understand the code. The entire word count code remains same. We are not changing anything here. What's important is we are actually doing something interesting in the word mapper. In the mapper, in the configure method, so this example will also serve you as a practical example for how to use configure method. We are reading a file from distributed cache called as stopwords.txt. So the file is called as stopwords.txt. Here what we do is we read the file line by line and we create an array called as stopwords. So we are creating an array called as stopwords. When the word count is happening, if the word is part of stopwords, it should not appear in the final word count. It should not appear in the final word count. That's the real idea. That's the real idea. So let's first run this with stopwords.txt, which is empty, and then we will look at how distributed cache can be used. So let's say the file that we are supposed to create is stopwords.txt. So let's first run this without any distributed cache. So let's run a word count program without using distributed cache. So we use Hadoop jar word count underscore old API dot jar word count Mapreduce input Mapreduce output without distributed cache. Let's run this program and let's look at a couple of words. What we've seen is we've got our output, but let's carefully look at the output, and then that will serve us better in the next example. So we will look at the output. So let's look at a couple of words. Let's say right now we are getting a word called zeal and youthful with double L. Now let's say we want to put these words zeal as well as youthful in our stopwords.txt. That means we don't want to see them in the output. And now let's run the code with distributed cache. So export jar. So we see a new jar is created. So we are sending stopwords.txt. And our output is Mapreduce output with distributed cache. Let's run this code. So we've got our output. Let's look at the output. So with distributed cache, what we see is zeal is gone and youthful with double L is gone. There is only one youthful. This is how you can use distributed cache. Distributed cache is an amazing facility for passing the lookup data. Distributed cache is an amazing facility for passing data as lookup data. So that is distributed cache. Let's summarize it now. Distributed cache is a facility that lets you pass lookup data to the Mapreduce program. The beauty is that in real world, the lookup data is passed to each slave before the job starts. Once the job starts, MapReduce program can read the lookup file from local path and execute the job. And the syntax for the same is Hadoop jar and the main class with the files option. So we can pass any kind of or any amount of lookup files. This is how we use distributed cache. This is how we use distributed cache. The next example that we are going to see is MapReduce unit, and along with that we will see local job runner mode. So let's look at what is local job runner mode. We've already discussed that a bit. We'll see what is local job runner mode, and we'll see MR unit. Now, by default, MapReduce program runs on HDFS. That means every small change you make, you will have to export the jar file. That's really unfriendly. What you want is, as a developer, you should be able to run this locally and test and debug it. What we are going to demonstrate right now is, instead of using HDFS, can I run my code directly from Eclipse and debug it? That is what we are going to do. And the mode that does that is called as local job runner mode. We've already theoretically discussed this, and practically we are going to see how to run your job in local job runner mode. So let's look at it. The first important thing is, for you to be able to run your code directly off the Eclipse will not be able to run this code on HDFS. So you will have to run it on local file system. So we'll have to create this input directory in local file system. So let's do that. So let's bring back the MapReduce input file on local file system and try to run this code. So we are trying to get MapReduce input here in home training. So here we have a directory called as MapReduce input, and we see a file called as shakespeare.txt. The next thing we'll do is, we will go to Eclipse and we will configure our code so that it runs on local file system. And it's extremely simple. Let's say we want to run the new API code. All we need to do is right click, run as run configuration, So here you can run it as, or you can define a new configuration. So here we click on Java application, and Java application you can create a new configuration. So let's say you call this configuration as local mode. You'll have to feed the project name, which is word count new API, and you can give the arguments. You'll have to give the full path. So we say home training MapReduce input. This is local file system, not HDFS. And home training MapReduce output. So these are the arguments we've given. Here we've given the main class, and here we've given the arguments. Just click apply and say run. What you see is that the job will run from local, in local file system mode. Now in case you get an error, this would be mostly because of the log4j library, that is slf4j library. This is a very normal phenomenon. So what you need to do is click on properties, add external jars, go to Hadoop, in the lib find the slf jar. These are the two jars, please include them. This is a common issue that you will get. Once you've imported them, again say run as, run configuration, local mode, and say run. What you observe is that your code is now running in the local file system mode. It's running directly from Eclipse, so you can debug it, you can run it, and the beauty is you can find Mapreduce output here. So you can perfectly run a Mapreduce code in local mode, not in HDFS mode, and debug it or test it. This is an amazing way to test your code, and it's a blessing for developers. So let's summarize it. This is local job runner mode. So a quick pause and let's quickly recall what we've done so far. We've understood what is old API, new API. We've understood differences, and we've run the code with old and new API. We understood that we can customize something from the command line using tool runner. So we can customize any behavior directly from the tool runner. We've then seen what exactly is distributed cache. It lets you pass the lookup data to your job. And we saw how to use stop words. The next thing we saw is local job runner mode that basically lets us run the job directly from the Eclipse VM or Eclipse IDE. The next topic that we are going to talk about is unit testing. We've already discussed that in depth in the theory. Now let's quickly look at how do you run unit tests in Mapreduce. How do you run unit tests in Mapreduce? So let's put a new project. So we already have code for MR unit. Again, there are no libraries, so let's get the libraries. And there is one more external jar, which is MR unit. Let's get that. Once we say okay, all the errors are gone. Let's have a code walkthrough of this. Now we have a word count code which is all okay, but here we have the unit test case class. We have set of import statements, and this is the name of our JUnit class. This is the name of our JUnit class. The intention of this particular class is to test. The intention of this particular class is to test our word count. It is to test our word count program. So here we have Mapreduce driver, map driver, and reduce driver. What that goes to tell us that we are trying our best, or we are trying to test mapper individually, reducer individually, and Mapreduce driver individually. Here we are writing 3 unit tests. In this particular example, we are writing 3 unit tests. So in the setup, we will initialize or instantiate a mapper and reducer. To our map driver, we'll have to tell that our mapper is this particular class. Our reducer is this particular class, that is word mapper and word reducer, and our Mapreduce code has this mapper and this reducer. So this is our way of telling map driver, that is the class that is supposed to test only the mapper, that word mapper is our mapper. To the reducer class we are saying some reducer is our reducer, and for the Mapreduce driver we'll have to communicate about both the classes. We start with test mapper. In test mapper we are saying that the mapper has input 1 comma cat dog. That's our input. And the expected output is cat1 dog 1. Now if you really see, the input to the mapper is cat dog, and the expected output is cat1 dog 1. So this is, we are expecting this to be a pass test case. Same is here. If we are testing a reducer, we'll have to artificially create a list, that is, let's say cat comma 1. That's what we are doing here. We are saying cat comma 1, and we are then expecting that the reducer will give output as cat comma 2. So this is like we are artificially creating a list which looks like cat comma 1, and the expected output is cat comma 2. And the third is test Mapreduce, where we have 1 comma cat dog. This is the input to the Mapreduce program, and the expected output, if we were to test the entire Mapreduce flow, is cat2 dog 2. So in this example we are trying, or what we want is we are trying to succeed at all the cases. So we say run as JUnit test, and everything is absolutely successful. Let's divert and we will see something failing. Let's say the input to Mapreduce is 1 comma cat dog, and the final output we say is cat1 and dog 2. This is going to be a failed test case. Right click, run as JUnit, and bang, it gives us error. It gives us error that the test case is failing. The test case is failing, and it clearly tells us that at line 49 we were expecting cat comma 1, but what we get is cat comma 2. That means this is a failed test case. The beauty is that this is automated. That means once you write this, every time you make a change, this unit test can run automatically, and you can always validate if a certain change has brought in or broke some other code. So unit testing is a very powerful concept. So let's look at what exactly is unit testing. So unit testing is a concept that talks about testing each and every individual piece of functionality, takes input and expected output and validates it against actual output, can run directly from Eclipse, and it builds on top of JUnit. So JUnit plus additional support for Mapreduce is MRUnit. That is how MRUnit works. So quick summary: old API, new API, tool runner, distributed cache, local job runner mode, and unit testing. The next we will see some advanced topics like partitioner, combiner, custom writables, and one of the use case, that is inverted index. Partitioner tries its best to be the load balancer, tries its best to be someone who would basically try to ensure that ideally everything goes 50-50, for example, or if there are 4 reducers, it would be 25, 25, 25, 25. Partitioner is the guy who basically decides which reducer a particular key should go to. And by default, the partitioner is hash code partitioner. We've already discussed a lot about partitioner in the theory section, and now it's time to get into the code. So let's understand how to go about writing partitioner. Here what we are going to demonstrate is how would things look without a partitioner, and what does partitioner bring to the table, and how does it basically bifurcate the data. So let's understand how to go about it. First we'll run the code without a partitioner, and then we will run the code with the partitioner. So we have a project called as word count partitioner. Let's first add libraries. Let's add external jars. Now in this example, everything is same like a word count. There are two major differences. Here we are hard coding that the number of reducers are 2, which is okay. And here we are specifying that what we want is a vowel partitioner. But first we are going to comment it out. Now this makes sure that this is nothing but a word count program. So we are using the default partitioner. Then it's as simple as a word count program. There is nothing different. Out here in the reducer, let's print the key. So the idea is that right now we have two reducers. We are using the default partitioner. That means it will use hash code partitioner, and we are printing out the keys. So let's understand which reducer each key is going to, and then we will write our own logic of partitioning. So currently we have commented out the partitioner. Let's export it as a jar file. Hadoop jar word count partitioner dot jar word count. Hadoop jar word count have underscore partitioner dot jar. Word count is the main class. Mapreduce input is the input folder. Mapreduce output with hash code partitioner is the output folder. So the job ID is 0012. What's important here is the job is successful. Click on history. What you see is that there are two reducers. reducers. So let's open them independently. So once we click on logs, we see that some keys have gone here, which are like, most of them are here with Y, Z, if you click on the entire log, so some integers are here, some words starting with A, so let's see some other words also. We have some words with W, P, M, L, I, F, E, C, B. When it comes to the second, same thing. We get certain words. So far the partitioning is hash code partitioning. That means we'll depend on the hash code, and based on that the partitioning would happen. Now let's go back to code and convey the main program that, listen, we would need our own partitioner, and the partitioner is called as vowel partitioner, which is implemented by us. Let's understand what is vowel partitioner. Vowel partitioner is basically a class that implements partitioner and works on a very simple logic. It's coded by us. If the word starts with A, E, I, O, U, go to reducer 0, else go to reducer 1. So if the word starts with A, E, I, O, U, everything will go to reducer 1, else everything will go to reducer 2. So the output that we see right now, it was based on hash code. When we run this program with a partitioner, we will certainly see that one reducer gets all the vowels and other reducer gets everything else. Let's do that. Let's save this. And let's export this as partitioner. Let's run this program with vowel partitioner. The job is submitted with ID 0013. The job is still running. Succeeded. We see 2 reducers. So this is a reducer. And what we see is everything is a vowel, A, E, I, O, U. That's it. Everything will be just A, E, I, O, U, nothing else. And everything else goes to the other log. Everything which is a consonant or an integer will go to this particular reducer. This is how partitioner works. This is how partitioner works. So quick summary. Partitioner is to load balance the keys, reducers. Can be customized and vowel partitioner. So that is all about partitioner. The next topic that we are going to talk about is combiner. What exactly is a combiner? Combiner is a mini reducer. It's basically something that reduces the traffic that goes across the network. And we've discussed combiner in a lot of detail in theory. In this case, we are going to talk about combiner from the practical perspective. Combiners are very easy to implement. In most cases, it will be zero effort. So a project called as word count underscore combiner. Let's add libraries. Let's add external jars. Now let's understand the impact of running the program without the combiner and with the combiner. Combiners are extremely simple to implement. All we need to do is set combiner class. In here, everything else is same, just that here we are saying please treat some reducer, this a reducer class, as a combiner. In the first run, we will not be using combiner and we'll see the impact, and then we will add the combiner and see the impact. So let's first comment the combiner. This is a complete word count program, no other change. Export. Combiner. So let's run a program without combiner. So we've successfully run this program and the job ID is 0014. Let's go to the job. Click on history. Number of reducers is 1. When we look at the counters, when you click on counters, what we see is the input records that were given to the reducer were 83,000 or 838,448. That's around 800k records. Around 800k records. That means there is fair amount of network traffic. What we are going to do now is we are going to implement a combiner. That is everything would be done on the mapper machine itself and there'll be no network traffic. So here what we see is there are around 800k records that have come to the reducer. Let's go to our code and just implement a combiner. Finish. Let's run the same code with combiner now. The job ID will be 0015. The job is still running. And the job is complete. Click on history, click on reduce, click on counters, and what you see is 800k records have been reduced to just 51,000 records. That's good 16 times of network reduction, 16 times of network traffic reduction. That is the power of combiner. That is the power of combiner. Combiner can heavily reduce your network traffic, and it's extremely simple to implement. In most cases, your reducer will be the combiner. So you just have to say conf.set combiner class some reducer. So that is combiner. So that is combiner. That is combiner. So a quick summary. We've started this video with, so this entire video is all about entire Mapreduce Lab. We started with old API, new API. We then spoke about the tool runner. We understood what is tool runner, lets you customize or override certain settings. Then we understood what is distributed cache, which is there for lookups. We understood local job runner mode, MR unit, and we've understood partitioner and combiner. The next thing we are going to see is custom writables. Let's talk about custom writables. In the theory section, we saw that not everything would always end up being a string or an integer. Sometimes you'll have to pass your own objects. And if you wish to pass your own objects, you are supposed to implement writable comparable. In this example, we are going to see how to go about implementing a writable comparable pair. So here we go with writables. We'll add libraries. Let's look at the code. There are a couple of, so it first starts with the main class. In the main class, we are setting the type as string pair variable. So the output key for the mapper and reducer, we are implementing a new type called as string pair writable. This is our own data type. It's not int writable but string pair writable. And that means in our map function we'll be sending across string pair writable, where we are sending a pair of two strings, and the implementation for string pair writable is here, which is string pair writable, where we have a constructor write for serialization and read fields for deserialization. Compare the strings. ToString is to what we want to return, and we have equals and hash code. So when we run this code, the mapper output is going to be string pair writable, as well as reducer output is going to be string pair writable. Let's understand this code. What we are doing here is very simple. We are trying to find which two words are coming nearby each other. So which pair of word is occurring together frequently. And here we have our own object. Let's run this code and understand it. Export. Writables.jar. Hadoop jar writables.jar. The package name is writables example, and the main class name is string pair test driver. Our input is again Mapreduce input. Our output is, so this is our own data type, and we want to write it in an output folder, pair output. So here instead of word comma 1, we are giving away pair comma 1, and this pair comma 1 is being treated as a new object. We've implemented that. Let's look at the output once we have it. So we look at pair output, and the file is here. What we are going to see is pairs instead of a single word or a single string. So output is a pair. So in the entire example, your and Sone has been used twice. Entire Shakespeare data. Your own is 3 times, and so on and so forth. So this is kind of word co-occurrence. 12 instances you and to is used together, and we've created this pair. This is string pair writable. It is not a default type. This has been created by us. That is how we go about creating our own custom writable. So we created a string pair writable in our example, and the last example for this particular video is inverted index. Inverted index is basically a kind of a very popular use case. We've already discussed this in theory. Let's see how do you implement it. We have a project which is inverted index cleanup. Let's add a library. You might be seeing an error for write tables, but let's just ignore that. What we do is, let's understand. So we have a main class called as line indexer. This program is basically going to give us a keyword in the file in which it exists. So the real idea is, in the mapper, we are extracting from a file split, we are extracting the file name, and we are emitting word comma location. In the reducer, we are simply showing all the locations. Now we are not removing the repetitions. Let's just run this code. Let's also looks like Eclipse has an issue because the code ran. Okay, it looks like we have deleted this. That seals the deal. So inverted index will basically give us keyword and the name of the file in which it exists. So we can call it as inverted index.jar. Line indexer Mapreduce input. So we run this code. Let's look at the output. What we see is which keyword is in which file. Yes, we are not removing the repetitions, and we can enhance the code by removing repetitions in the reducer. But that's the core idea of inverted index. One thing that this example tries to demonstrate is, in your mapper, from a block you can extract a file name. From a block you can extract the file name from the metadata. So this is how inverted index are built. And that brings us to the end of this video. Let's quickly summarize everything that we've seen in this video. We started this video by talking about Mapreduce, what Mapreduce does, what are the APIs available, old API as well as new API, how new API is just a signature change. We ran old API as well as new API. Then we moved our focus to tool runner, which talks about customizing a certain default behavior of the cluster. We changed the number of reducers. We then moved to distributed cache, which is basically used to pass on the lookup data. Then we looked at local job runner mode. Local job runner mode is a mode which is ideal for developers to debug and test their code. You can run your code directly from Eclipse, no need to export a jar file. The next is MR unit. In MR unit, we saw how to unit test your code. We move to partitioner. In partitioner, what we saw is how to load balance the data, and we used Vowel partitioner. In the combiner topic, we saw how to reduce the network traffic, and then we saw how to have your own objects as writables. We created string pair writable, and we also saw how to implement inverted index. So this video basically spoke about literally every topic that we discussed in theory. In the next couple of videos, we will see how to write a user-defined function in Hive Pig and how to connect Hadoop to Pentaho. Thanks for watching this video.